Okay, so here's our case study for this week, and it's this Berkeley example we've been looking at. And just to remind you, the idea was that Berkeley was taken to court because they seemed to be favouring males over females with their admission policy. And the question is, well, were they? So we're going to have a look at the data and address that. So let's go over to R. First of all, we will read in my data. There we are. Oh, packages written. So this is what our data looks like. We have the department, which we've denoted as A up to F. We have male and female, and we have how many admitted and how rejected. So for example, in department A, altogether for the males, 512 were admitted and 313 were rejected. So as always, let's have a quick just look at the numbers. This one's probably not as good. You've got sort of what we call a frequency table here, so you don't see stuff quite as interesting. There's not a lot to see there, but what I'm going to do is we're going to do some plots. So this is a complicated one. Let's break it down. I'm going to take my data and I'm going to first of all group it by sex. And I'm going to add how many of the males and females were admitted, how many were rejected. And then I calculate the proportion that were admitted. And then I just calculate a quick 95% confidence interval for that proportion. Then we're going to plot it with some error bars. What does this look like? It'll look like this. So we've got on the x-axis female and male. We have the proportion, we've got 95% confidence intervals. And you can see it looks like there is a hell of a lot of more probability of being admitted if you're male compared with female. And this is why Berkeley were taken to court. It looks quite obvious there. But what we're going to do next is we're going to do exactly the same thing again, but this time on our x-axis we're going to have department. And the thing you first will notice is there's a lot of heteroskedasticity here. That is, the rates of being accepted into different departments is very different. Here, these two, A and B, you're very likely to be accepted. Then you've sort of got these three here to some extent, C, D, and E, which is not pretty bad, about 0.3. And then obviously this department here is very hard to get into. A lot of people rejected for that. The other thing I'm going to do is I'm going to do exactly the same thing now, but I'm going to do both department and sex, and we're going to colour them. So what we've got here, you can see department A, there is definitely what looks like a split between male and female, but it's female that's much more likely to get in. Here they're about the same. Here they're about the same, about the same, about the same, about the same. So any time we see any real difference is in a department A, and that seems to favour females. Okay, so let's think about how we can analyse this data. So we're going to do a logistic regression. We've got our success and failures. We're going to do a model where we just have sex, a model where we have sex and department, which remember is called the common odds ratio one. And we're also going to have sex and department and an interaction term as well. So let's fit all these models. So we've got the first one here. If we just looked at sex on its own, there definitely seems to be a significant effect of sex, and because this is a positive number and this is male compared with females, it looks like the probability of success is increased if you are male compared with a female. So again, we see this idea that there might be some sexism there. But the next thing we're going to do is we're going to actually say, well, let's actually add in department. So once we add in department, suddenly you notice that the sex term is no longer significant. Basically, it's the department that's having that big effect. We saw that heterogeneity there. The one we do is we do the full interaction model. And one thing you should notice that there's a subtlety here. Like, you might just go straight to this table, which is fair enough. But just look at a couple of things. First of all, notice all the deviance residuals are 0. And notice here, you've got something very small. Basically, I don't want to use the word overfitted, but you've fitted it exactly. Basically, your estimates of each of these coefficients are exactly the data you observe. There's sort of no noise in it. We could call it overfitted, but basically you've got to be careful with this model. But it does fit very, very well. And you can see there's significant differences as an interaction between the probability of getting admitted and the department, which we saw before. So we could say, well, which is the best model? We could first of all start by comparing our largest model, which is the one we've just done, and the next smallest, which is M2. And you can see that there is a significant difference between them. So ideally, you would like to have that interaction term, although I'd be a little bit reticent because you are overfitting there. But, you know, it is the better model when it comes to fitting. You could ask, well, we could compare model 1 with model 2. And yeah, there's a significant problem if we drop department from there. And we see that we need that. The other thing you could do is you could have a look at AIC. We haven't done AIC later. You should have seen it in SME. And we're going to cover it again in later weeks. But remember, rough rule of thumb, the smaller the better. And you can see here that full interaction model fits the best with a nice 92. Well, you can say, well, how could we have picked this up another way? Would we have picked it up if we had just done because we could have just blindly gone and just done logistic regression of gender or sex and been concerned and say, well, this seems fine, but, you know, obviously there's a favoritism for males. So what I'm going to do here is I'm going to grab the Pearson residuals for all the models. So all this is doing is, if we have a look at this, is I've just added the residual for each model. What I'm going to do now is I'm actually going to plot the residuals versus department for each of these models. And let's have a look. And hopefully this, remember, if our model's good, the residuals should basically sit around 0. And you can see, if we'd looked at our model and we had ignored department, when we looked at our residual versus department, you can see there's still a lot of relationship there. There's a lot of heterogeneity. These aren't all line. Once we take into account department, it's not a problem. And again, here they're just too perfect. There is no residuals. They all sit at 0. So even if we hadn't thought about department, we probably could have started looking at our plots and seen this heterogeneity against department and go, oh, there's something here we need to have it in. And it is a good indication that if there's strata there, you should actually take them into account. You see it to some extent, not as much, if we actually look at our residuals. You can see here you have a lot more spread from males compared to females. So even if you didn't even have department in there and you looked at this plot, you'd be looking and going, I'm a little bit worried there seems to be some heteroskedasticity in here. We need to go and find out and explain this a bit better. So there's a Berkeley. We see that you definitely need department in there. Once you have department in there, you find there is no longer an effect of gender. Okay, so that's it. Next week we get to Poisson. See you next week.